Welcome to Real Physics. This is about the Machian Gravity Meeting recently held in Bonn with Dennis Braun, Jonathan Fay, Jan Preuss and myself. The talks and discussions are a little bit more technical than usual, thus if you're interested in the details I encourage you to look up my variable speed of light playlist or the papers linked in this video. Enjoy watching. Yeah, welcome again to this session. We will listen to a talk by Dennis Braun about Solitons. And curious about his findings.
Yeah, I'm talking about a Soliton model for elementary particles. And I came in contact with this idea when I visited Klaus Hasselmann some years ago. And he showed me this. And I think this is a very good alternative to the usual approach to the phenomenon of special relativity. And yes, I will show you this model in the following. Yeah, as we had already agreed here, that gravity and inertia should be unified. And this brings up some consequences, which more or less directly lead to the Soliton model of elementary particles. As I told yesterday, in Trader's mechanics, we have a unification of gravity and inertia, and the inertial mass of a particle is given by 2 times the gravitational potential over c squared times the gravitational mass. And this implies that inertial mass is not an independent property of particles, but a consequence of their gravitational mass and the gravitational field. This, so to say, strips the mass of its special standing outside of any fields, because the particles no longer have any inertial mass in the absence of any fields. And this is very different than in standard theories, because in standard theories, particles have an inertial mass whether there are any fields present or not. It doesn't make any difference. And so inertial mass really is more fundamental than the fields. And this is no longer the case when you unify gravity and inertia, because then mass really only makes sense in the presence of a gravitational field, because the inertial mass is a derived quantity from the gravitational mass, and the gravitational mass only makes sense in relation to the gravitational field. And this, so to say, puts mass and the gravitational field hierarchically on the same level, that one does not make sense without the other. So you have no gravitation without mass, but the concept of mass also does not make sense in the absence of gravity. And one can draw a conclusion from this, that mass is a special manifestation of the gravitational field. And if one recalls what the properties of particles are, one searches for some localized, shape-preserving, propagating energy clump in the gravitational field, which remains invariant upon collisions, which remains its shape when it collides with other particles. And this is exactly the properties which solitons have. And yes, this is the reason why one should search for soliton solutions to the gravitational field equations as a model for the elementary particles. And the mass is then given by m equals E over c squared, where E is the energy of this lump in the gravitational field. Yeah, what is a soliton? As I already said, it is a localized self-reinforcing stable propagating wave packet which preserves its shape under collisions. And it owes its stability due to the balance between dispersion and non-linearity. And so solitons are really an intrinsic phenomenon of nonlinear partial differential equations. You cannot have soliton solutions in linear equations, you need nonlinear equations, because otherwise the wave packet would not be stable, because it disperses and you have no nonlinearity to balance this dispersion. Yes, and solitons also exhibit wave and particle properties, because it is a wave, but it is localized and therefore has particle properties, and this gives a approach, or a natural approach, to the wave-particle duality, and I will talk a bit about this later. Yeah, an example is the Korteweg-de-Vries equation. This is a Soliton equation, or equation which admits Soliton solutions. And it describes surface waves in shallow water. And you can see that the second term is the nonlinearity and the third term is the dispersion. And it means solutions of the form u of x and t is velocity half times hyperbolic secant squared of square root of v over 2 times x minus vt minus x0. And yeah, the x0 is the initial position, so to say, and v is the velocity. And the solution is plotted on the right side for x equals vt plus x0. Yeah, one can see the envelope of the soliton, and this wave packet propagates right if v is positive, and it preserves its shape while it propagates through space. Yeah. Now, how does one get solitons in the gravitational field? One can consider the relativistic field equation. D'Alembert phi equals 4 pi times g times rho, and rho is the energy density. This is the standard linearized equation for the gravitational field. And if we now assume that mass is part of the gravitational field itself, we can write the right-hand side as some function of the potential itself. Just for practicability reasons, I have written it as derivative of some function v, and then we obtain a nonlinear wave equation in the gravitational potential. And it admits traveling wave solutions of the form phi of x and t is equal to phi of gamma times x minus vt. And this actually, in principle, allows to explain all the phenomena of special relativity as properties of the elementary particles, or as consequences of the elementary particles, which are soliton solutions to the above equation, in Euclidean space. So you don't need to let space contract or time be dilated when you move, but it is a consequence of the solitons itself.
Gamma is just the Lorentz factor.
Gamma is the Lorentz factor, yes, exactly. So we begin with length contraction. The elementary particles provide elementary rulers, and their length can be characterized by a certain alpha decay of the envelope of the soliton, by that at some length, L over 2, the envelope of the soliton has decayed by a factor of alpha, and this you can actually solve for this elementary length L. And you gain L is gamma to the minus 1 times 2 times inverse of phi of alpha times phi 0. And for a resting soliton, this yields your rest length, 2 times phi to the minus 1 of alpha times phi 0. And for a moving soliton, you gain the same, but with a factor of gamma to the minus 1 front. And this is just the length contraction formula. So your standard for the for your elementary rulers is contracted by a Lorentz factor of gamma to the minus 1. And since all macroscopic rulers are composed of elementary rulers, because all matter is built of elementary particles, they inherit this behavior from the elementary particles. And so you gain length contraction. Now the relativistic kinetic energy formula. The field energy is a well-known formula. And you can actually calculate the energy for two cases, for a resting soliton and for a moving soliton. And if you use the equation of motion, or the field equation we had on the previous sheet, then you can calculate the rest energy, and you gain something like 2 times the integral over the whole space of the potential, and this is your rest energy. And for a moving soliton, you can again with some substitutions, and by using the field equations, you gain gamma times the same integral. And so for moving soliton, the energy is gamma times the rest energy. And yes, if one uses the mass definition, which I talked about earlier, that m is defined as E over c squared, then you gain the formula for the relativistic kinetic energy. This an interesting thing to notice here is that this indeed holds independent of the choice of the potential. So whatever you choose for the dependence of the potential on the phi, you gain this behavior. Now, for time dilation, to properly describe time dilation, you need oscillatory solutions. These are the so-called breather solitons. And this is a special kind of soliton solution where the envelope oscillates. Yes, then again, like the length contraction, the elementary particles provide elementary clocks. And to show how this works, I will choose some kind of toy model, but it is not the only model which has breather solutions. It is a more general phenomenon. But I will demonstrate it here for the Sine-Gordon equation. This was actually done by a guy called Günther in 1988, who showed how time dilation can be derived from this. And consider therefore the general breather solution to the Sine-Gordon equation, which is given by this formula. And if we look at the envelope at x equals v times t, then it oscillates with the frequency omega times omega 0 times gamma to the minus 1. And a clock at rest then ticks with the frequency omega 0, and a moving clock ticks with the frequency omega 0 times gamma to the minus 1. And this means that a moving clock ticks slower by exactly the relativistic gamma factor than a clock at rest. Yes, and again, like with the length contraction, since all macroscopic clocks are composed of elementary clocks, they inherit this behavior from the elementary particles. And this then gives rise to time dilation. Yes, now to the apparent constancy of the speed of light. An important difference to the standard theories is that the speed of light is not actually a constant, but you only measure it as a constant when you use your co-moving rulers and clocks. But other than that, the speed of light just behaves like a usual vector in the three-dimensional space. It's just obeys the standard velocity addition formula. And it just appears as a constant in whichever frame you measure it. This I will show now. Consider therefore a test section of rest length x0, and the time needed for a light signal to travel back and forth in this test section is 2 times x0 over c0, where c0 is the speed of light measured in is this speed of light. And then if we measure the speed of light, we gain 2 times x0 over t0, and this yields c0 in the rest frame. Now we do this again in the moving frame, which is moving with some velocity. And then, like I said, the speed of light will just obey the usual vector addition. And so for the, if it travels the way forth, it has a velocity of c0 minus v, and for the way back, it has a velocity of c0 plus v. And then we calculate for the times it takes to travel forth. It is delta x over c0 minus v, and for the time back, it needs delta x over c0 plus v. And then one can calculate this total time that it needs, and it just yields something like 2 times delta x over c0 times gamma squared. But now also the test section is contracted by the inverse of the Lorentz factor, as I already have shown. And also, if we measure the time with co-moving clocks, then because they tick slower, the time that we measure is also reduced by a factor of gamma to the minus 1. And if we plug this in what we measure for the speed of light, 2 times delta x0 over delta t, then we see that the both gamma squared factors cancel each other out, and we remain with c0 again. So in the moving frame, we measure the same speed of light as in the rest frame, although the speed of light is not actually the same, but depending whether it travels back or forth, it is c0 minus v or c0 plus v, just like a usual speed would be too. Yes, this for the phenomenology of the special relativity. Once again, it is here not a consequence of space and time behaving differently, but just a consequence of the elementary particles. Yes, and now also for the, we come to the Soliton interaction. One, of course, does not only want to recover the phenomenology of special relativity, but what one also wants to actually do something like an n-particle model or so, that particles interact and the particles can collide. And yes, therefore we have a look now at Soliton interaction. Interestingly, is the interaction between the solitons via their fields is included in the soliton solution itself. This is a property of the so-called multi-soliton solution. So almost all equations which have soliton solutions also have multi-soliton solutions, which describe an arbitrary number of solitons eventually colliding and interacting via their fields. And to demonstrate how this works, we again work with the Sine-Gordon equation as an example. This is the two-soliton solution, which is shown there. And this describes two solitons propagating and eventually colliding. And we will now have a look at two non-relativistic solitons. Of course, this equation is full relativistic, and one could also do this full relativistic, but to simplify the math, I have taken the non-relativistic limit to show how it works. Yes, on the right side it shows the energy density as a xt diagram of this two soliton solution, and one can already see that these two solitons collide. The initially fast soliton is the left one, and the slower soliton is the right one. And in the middle they collide, and then the faster soliton is afterwards the formerly faster soliton is now the slower one, and the slower soliton is the faster one. And the speeds are actually mirrored. So the slower soliton has exactly the same speed that the faster soliton had before the collision, and the slower soliton has exactly the same speed that the faster one had. And so this is the same what happens when two particles of the same mass collide with each other. And yes, the trajectories are given by this formula. And if one takes the limits of t to minus infinity or t plus infinity, then one can actually see what I just said. What is an important difference here to usual particles colliding is that it is not a collision of solid balls, but is a continuous transfer of momentum via the fields of the solitons. So they do not hit at one particular point where they exchange their momentums, but they continuously interact via their fields when they get close to each other, and the end result is done the same as the one of an instantaneous collision. So one can see that the interaction via the fields and yes, the resulting trajectories are all encoded in the two soliton solution of the in this case the Sine-Gordon equation, but it also holds for all other equations which have soliton solutions. So, and this also applies to arbitrary n. One does not have to restrict oneself to two solitons, but one has in general n soliton solutions which can be found analytically. And then the n-soliton solution is, so to say, the relativistic generalization of an n-particle model like the one of Trader that I presented in my last talk, and describe the motion and interaction of n-solitons or n-particles in just a single solution to the Soliton equation. Below I've shown an example for such an n-soliton solution, again for the Sine-Gordon equation. It is a bit more involved if one writes it out, but one can give it in a closed form, which I find really surprising, because this expression there's really a lot of physics going on in this expression, and one can write down it just as one closed solution. And again, all the trajectories and the interactions are encoded in this solution. And yes, maybe as a final remark, a very interesting consequence of this also is since the trajectories of the particles are already encoded in this solution, not only the fields are included, but also the solutions to the equation of motion are already present in the Soliton solution. And one can actually derive the trajectories of the single particles then by finding the maxima of the energy density, and one can solve for the trajectories algebraically, but one does not need to solve a differential equation anymore, because one has already done this in finding the Soliton solution. Yes, with this I conclude my talk about the Soliton model, that we have seen particles are solitons in the gravitational field, or maybe more general, a unified field, which would then also include the electromagnetic field, but then of course one would have to find, one would have to explain charge as a consequence of the field too, and I do not have any idea or come across any idea how one should do this, but it is a somewhat obvious conclusion that the electromagnetic field really should also be included in this one unified field, which has the Soliton solutions. And the solitons exhibit wave and particle properties, and this gives a possible approach to quantum mechanics. And the particles themselves give rise to all the phenomenology of special relativity, and therefore one also gets relativity out of it. And all this is done in Euclidean space with normal vector addition, and one has no changes in space and time, but they just remain as the background, the passive background in which the laws are formulated, but which is neither act upon nor does it act upon the particles. And also mass is explained as entirely of gravitational origin, or again of this unified field. And it is a special manifestation of the field energy, and there is no obscure Higgs field needed to explain the origin of mass. And I think this could be a gateway to a unified field theory, or to a unified theory of fields and particles. Yes, thank you for your attention, and this was my talk on the Soliton.
Okay, this is okay. Thank you, very intriguing. I'm kind of bursting because it's very, very interesting. Well, basically one big comment and a big question. The guy you mentioned, I think it's Helmut Günther. He was a lecturer in Münster.
Yes.
Yes. And I visited him in 1994 because he was doing that kind of research, playing with the idea that elementary particles might be represented by Soliton solutions, or more generally speaking, defects in solids. And Günther's work was inspired very much by Gerhard Kröner, who was a professor in Stuttgart and dealing with the theory of dislocations, and he was, I guess, the first one who advanced the idea that elementary particles could be described by defects in solids, especially focusing also on the property you mentioned, because you have this wave-particle duality popping out very nicely. And the relativistic behavior you also mentioned, I guess, was first proven in a paper by Frank in 1949.
He proved it for the sine-Gordon equation, yes.
Mm-hmm. Yeah.
Yes.
Yeah. So, what question is that you're considering these solutions, but what is it what oscillates? I mean, we're talking in mathematical terms. You have a fiber bundle. What's the bundle and what's the fiber? The bundle should be your usual space-time, 3 dimensions, Euclidean space. But you're considering scalars or complex valued functions or distortions in a material, or I guess in the very end we need something at least with dimension 3 to get some interesting physics. I want you to comment on what's the solution and how to bring it to the quantitative level of considering the extension of the particles and so on.
Of course,
it's very much.
First, a comment. Of course, the sine-Gordon model is one-dimensional, and it is, as I said, it is just a toy model, and of course the full model needs to be 3-dimensional, and but finding Soliton solutions is actually an active field of research. So there is probably some math to be developed, especially in 3 dimensions. And yes, for the other thing, what oscillates, the particles are really a clump or soliton in the gravitational field. So there is no additional solid or crystal or something like that which should be postulated, but the argument is that it is the gravitational field itself, or some unified field which contains gravitational and electromagnetic field, in which those lumps or solitons are the particles. And those lumps are also the ones which oscillate, because this is just a special form of soliton solution which has this oscillatory behavior. And you actually need this to find, to describe time dilation.
So are they some kind of gravitational wave?
Yes, so to say, some non-linear gravitational wave.
And it's because of the non-linearity of gravity that this can happen?
Yes, this is also quite interesting, because you actually need non-linear equations, and the gravitational field just is non-linear, and this is an additional argument why it should be the gravitational field.
Well, if I may interject here, okay, you need non-linear equations, but not necessarily that means that you exclude electrodynamics. I mean, we know that electrodynamics in the first approximation is linear, but who knows? I mean, if you go to variable speed of light, you need to modify also Maxwell's equations, which potentially could become non-linear. So, I mean, all this is still open to creativity.
To say the speed of light, as the rest speed of light, or the speed of light when you rest with respect to the field, really is a constant here, and it does not vary with position, at least not from what I can see now. And about the inclusion of electromagnetism, as I said, probably in a unified field it would be included, but I don't have any idea or came across any idea how the charge would then be explained from the field, and therefore I have just left this open, and maybe it already works just with the gravitational field, one is able to find a theory only including the gravitational field. I do not know, as you said, this is open research.
There's something else a bit conceptually difficult here, which is that the mass is coming from the energy of the soliton, related to like its wavelength, I suppose.
Just the
frequency.
Just the field. If you just integrate the
the
energy density of the field.
Yeah. So there's this energy density of the field, which is giving its mass. But then its mass is also meant to be influenced by the other solitons, the other particles, the rest of the particles in the universe.
Yes, of course.
And so the field has a strange property that other solitons are somehow increasing the mass of a soliton over here.
Of course.
The presence of other
This
solitons.
is what we have with Mach's principle yesterday already in the classical model, that the inertial mass is proportional to the gravitational
exactly.
potential.
But then can we make that somehow a property that comes out of the property of the field itself? Right? Can we make that somehow
Yes,
a direct property of the field?
yes, of course. This is encoded in the Soliton solutions to the field equations.
Oh, so the n-solitons have this kind of like self-reinforcing effect.
Yes, exactly.
Oh, wow.
This is
Okay.
the n-particle dynamics is really encoded in just this one solution.
So so your n-particle solutions encode Mach's principle.
Yes.
Okay. Wow. That's really interesting.
Is Jan had a comment?
Can you show us the slide again where you calculate the energy or integrate over the energy density? I believe it was somewhere.
Yeah.
I'm still wondering a bit where exactly the non-linearity comes in. Perhaps you can go back a few slides where you...
It is
here.
in the function v.
Right, so but you said v can be any function.
Yes.
So what happens if it's a linear function?
Then you don't get soliton solutions. But actually, the equation.
But you still manage to reproduce the relativistic effects, right?
Yes, this is just no only this for the relativistic kinetic energy. This formula indeed comes out independent of the choice of the potential. This is quite remarkable. But in order to obtain soliton solutions, you need a non-linearity, so it would not work with the linear equation.
So if it was linear, you would just have sort of photon-like solutions that...
Yes, then you gain the Klein-Gordon equation for linear.
Right. Yeah, this is really interesting. And very happy with the conceptual framework as well.
Yes, so was I.
I mean, already the fact that special relativity, all these effects come out of
Yes.
Solutions is stunning.
Yes.
It's not widely known. No. I guess this even Dicke talks about this in the introduction. He touches this intention.
This I don't know. I've just read the papers you mentioned from
Yeah.
Günther and from Kröner and from Frank. I've read this.
Mm-hmm.
So Dialect has also done a video, I think, on this topic about how special relativity is just a general feature of wave.
That would be great, yeah. He is a fantastic visualizer.
Yeah, exactly. And I was also going to say something. So, if special relativity is understood according to this and what many other people have said as a property of as a property of a field and not like a property of space-time, right? Then this implies a unified field already, because special relativity is common to all of the forces.
Yes. And you don't need to make mechanics Lorentz invariant, but mechanics is already Lorentz invariant because it actually, the particles are derived from the field itself.
And they're all derived from the same field, which is the key thing that makes
Yes.
makes
Exactly.
invariance.
Yes.
Yeah.
Exactly.
You can't get past Lorentz invariance.
So if you would go back to the early 20th century or late 19th century, one would not have to bother anymore that Maxwell's equations are Lorentz invariant and mechanics is not.
Exactly.
Because the Lorentz invariance of mechanics really is just a consequence of the Lorentz invariance of the
And
Maxwell
this, I've
equations.
been meaning to write an essay arguing that exactly this, that the real insight of special relativity is that all of the forces and all of the matter that constitutes our bodies and everything is generated as part of the same field,
Yes.
rather than the general interpretation that space-time is.
But this is not true in special relativity, because in special relativity you have to artificially make it this way by postulating that space and time behave in a different way.
But I think you can still use like the Minkowski metric, just interpret it not as space-time, just as
Maybe
this relativistic field effect.
Yes, maybe there exists a one-to-one correspondence where you can translate it into the
Exactly.
into
It
the
just depends like how you interpret the mathematical symbols, and but it's the same math, I think.
But this again is very more specific, because for this to be true, you need a very specific model for the elementary particles.
Right.
While in the standard formulation of special relativity, the particle model is completely arbitrary.
Yeah, exactly.
Have you thought any closer about the relation of this to conventional quantum mechanics? So you have already talked about the energy of a soliton and it being usable as an elementary clock and elementary meter stick or whatever, and in quantum mechanics you have Planck's constant, which relates frequency to energy and wavelength to momentum and so forth, and this would be nice if somehow we could get an explanation of Planck's constant out of that.
Of course, but I don't have dug deeper into it. Actually, I just started with this like 2 months ago or so.
Probably you cannot include that in a one-dimensional model, because an essential feature of H is angular momentum, and so you need
just
three-dimensional solutions.
What is just I think striking is that you gain this wave-particle duality just by itself, and this already hints that quantum mechanics really also is a consequence of such a model. And also, you have waves, and standing waves have modes, and this would naturally give rise to something like quantum numbers or quantization. And so I really think this also opens a door to explain quantum mechanics in some way, like a pilot wave theory, or what Bohr and de Broglie, not Bohr, Bohm and de Broglie did.
Well, I guess we need an encompassing picture here. You certainly cannot separately understand quantum mechanics without touching electrodynamics. So this would be a wholesale picture, but even the more difficult, of course. Yeah, I had also speculated a long time about these parallels, not only the wave-particle dualism, but there was also some nice relation to Maxwell's equations if you look at such continuum mechanical models. And,
yes.
I have heard about the paper in Zentralblatt der angewandten.
Yes, I have read that.
It's worth mentioning also that the uncertainty principle is a generic feature of wave mechanics as well.
Yes,
right.
Exactly.
So you have the uncertainty principle, generic feature of waves, and then the Lorentz transformations as being a generic feature of waves. So it seems these are like just things that come together. Right?
Yeah.
Exactly. This, like you said, also like, I didn't invent the equations myself. Most of them I just used and did some calculations with. But I really like the conceptual framework. When I read this work by Günther, who did it with the Sine-Gordon model, it was just, maybe you know, sometimes you have these moments where you read something and just instantly know this is true.
Yeah, he was also kind of fascinating. I don't remember exactly whether he was a pupil of Kröner's or...
Interesting is also that Günther was closely related to Trader, because Trader encouraged him to do this.
From East Germany.
Yes.
Günther come from
Yes.
Britain. But he managed to come to the West early.
I'm not sure about this, but at the end of his paper...
It was 1994 already, okay.
At the end of his paper, he thanks Trader for his encouragement to do this. So really, Trader also had this
That's very cool.
idea that this could be something worth publishing.
Do you think they were less influenced by the Americans?
I really think this is true, because I think it is not a coincidence that the isolation in the German Democratic Republic and these very different ideas are not a coincidence, but it is.
Yeah.
I think this is there is something behind it.
Yeah, I mean, we're definitely working in the European tradition here, I guess. Not in the
Lived a little longer.
build great
Republic.
big apparatuses in the.
But this is also really crazy what you're saying, like that the n-particle model produces this Machian effect.
Yes.
That's
I mean,
really
this is
wild.
this. To be completely honest, of course, this remains to be shown. I have no exact three-dimensional model.
Right.
But if you write down this is a calculation I did by myself. You saw the trajectory of the two solitons scattering at each other. This you can inversely calculate the potential which give rise to this motion from the equation, and then you gain that the potential is actually almost the same that the Trader also used. It is something like 1 plus the relative velocity squared over, and then something like hyperbolic cosine squared of the relative distance, something like that.
So there's some kind of like interaction potential. But
Yes, and it is velocity dependent on the relative velocity. So this potential which comes out in the lowest order non-relativistic really is Machian. It depends only on the relative quantities. Again, this is only a toy model. I'm not sure if someone has found n-soliton solutions to a general three-dimensional equation.
yeah.
Because nonlinear partial differential equations are hard to solve.